Hello. Mhm. Hello. Hello, can anyone hear me? Hello. Hello.
Hello, good afternoon. I think I can hear you.
Can anyone hear me?
Yes, I can. I can.
We can hear you.
Hello, can anyone hear me?
We can hear you.
Yes, we can.
Hi, can anyone hear me? What's wrong with my speaker?
I don't think his audio is connected.
Okay, I can hear someone speak. Can you guys hear me?
Yes, we can hear
Yes,
you.
we can. We can.
Okay, sorry about that. Think, are you hearing any background voice from my end?
Not really.
Okay, all right. Welcome everyone. Welcome Captain Michael Kenneth, Sonyedara, Vara, Solulupe, Courage. Yeah, welcome everyone. Today is day 3 of the stage E live coding session, and it has been an interesting journey so far with our whole time series projects. And yeah, we're just going to continue from where we stopped in our last class. But before that, we'll go through some few slides just to have a theoretical knowledge on some terminology or process that involves time series predictions. So let me quickly share my slide because we're already 9 minutes down. Okay, can you see my screen? Can you see my screen?
Yes.
Yes,
Right.
we can.
Okay. All right. So today we want to look at wrangling time series data. It's more like the process you need to follow, right, to make sure that you arrive at a an accurate result and yeah, good predictions. We want to look at wrangling a time series data, the process or what it involves, the things you can do. Okay, so that's going to be our focus for today. Data cleaning, the transformation, the resampling and handling missing values. All these steps are actually crucial for preparing our data for analysis and forecasting. So we have the data cleaning. We all know what it is. Data cleaning is about finding and fixing errors in our data sets. And clean data is essential for accurate analysis. Then common issues we need to address includes duplicates, outliers, and inconsistent data. Right? Duplicates are repeated entries that can skew our results. We have duplicate information, it can skew your results, right? Then we have outliers. So those extreme values that don't fit the pattern of the rest of the data. So I usually give a scenario, say you have a store and let's say the sales or the amount of sales you usually make is like 100, 200, 400, 500, 200, just within the range of 100 to 1000. Let's say that's the number of sales you usually make like for one entry. Then all of a sudden someone just came one day and just bought something of let's say 10,000. I mean, 10,000 is even too high. Let's say 5,000. If you try to visualize that data, 5,000 will be seen as an outlier because it's far way outside the usual range of cells you usually make. So yeah, that's outlier. And yeah, if you try to look at, let's take for instance, the average of your cells, including that 5,000, it's going to affect your average value, right? It's going to make it big. But the moment you take that outlier out, you now then have an average that makes sense and aligns with your current with your data. So outliers are actually important and they need to be treated. Inconsistent data refers to entries that do not match the expected format or range. Say you have a date column and it is a string, which is like a norms in most of our wrangling and cleaning process. Or you have an integer column and it's a string. Yeah, that's inconsistent data. Then we have the data transformation. Again, in case you have any question, you can feel free to drop it on the chat box or you call my attention. We have data transformation, which involves changing the format or structure of our data. So we have the scaling, right? So adjust data values to fit within a specific range. It's usually 0 to 1 or -1 to 1. So you bring it to a particular scale. Normalization adjusts values measured on different scale to a common scale. So you have the quantity column, and it's usually, let's say you're dealing with a small store, right? And it's usually 1, 5, 6, 7. And you have your sales column, which is values in 100, 200, and 1,000, and the rest of them. So what you can do is to normalize it, bring it to a level that both of them are, they can relate with each other, right? That's normalization. Log transformation helps reduce skewness and stabilize variance in data. All these transformations are actually helpful in improving performance of our models. So these are things that can actually apply on your time series data. Then we have the resampling. I think we touched this in our last class where we did some downsampling because the forex data we are working with is it's on a daily granularity. It's on a daily level. So we downsample it to a weekly level. And yeah, that was actually helpful in terms of eliminating some missing values, right? So yeah, we have resampling. This is changing the frequency of our time series data. We have the upsampling, which increases the frequency, like converting monthly data to weekly data. So you are increasing the granularity of your data. You're making it much, right? Then we have the downsampling, which is like decreasing the frequency, like converting daily data to monthly. Like in our case, we converted it from daily to weekly. Then yeah, I think that's the two method we have for resampling. So resampling helps in aggregating data for analysis or filling in missing data points. Let me give a scenario. Say you have a Monday to Friday. Let's take a month, for instance. Then out of the 4 weeks in the month, let's say the first week there are missing entries for Tuesday and Wednesday. The second week, let's say there's just a single missing entry, let's say for Thursday or Monday, whichever one, but it's one missing entry. So if you try looking at this data on a daily basis, you obviously see all those missing values. But if you should aggregate it to a week basis, let's say week 1, week 2, week 3, and then perform an aggregation. Like in our case, we did average. So the moment you do that aggregation, you bring it down to that weekly, you won't see those missing values. I mean, week 1 will obviously have a value, 2 have a value, so you will not see those missing values. So yeah, that's actually what it means by filling missing data points. I just hope you understood that explanation. Yeah, handling missing values is actually crucial because gaps can affect our analysis. I think there was a plot too that I talked about in our last class where it was showing a cut, a break. So all those break was as a result of missing values. Let me see if I can share. Yeah, let me see if I can share my entire screen for a few moments before I take it back. I'm coming in. Let me just share my entire screen. Exactly. Okay, so let me see if I can look at it. I'm just trying to show you what missing value can cause in our data sets. I don't seem to find it here. Okay, just give me a sec. Mm, okay, I just had to turn to the exchange. Yeah, this was the one we were working with in our last class. All right, so this point you see here is actually as a result of missing value. Sorry, let me zoom in. Yeah, all these breaks you're seeing here, all these breaks you're seeing here, it's actually as a result of the missing value. Yeah, so they actually, though we are looking at it on a weekly basis. Yeah, I think it would have made more sense if it was on a daily basis. But when you see, whenever there is a break in that, when in your line, maybe you're visualizing just one column, it's actually as a result of missing values. But the moment you eliminate those missing values, you always have a straight line. Okay, so let me just go back to my presentation. Shifting. Okay, coming now. Oh no. Oh, boy. Yeah. Sorry about that. So yeah, we need to handle those missing values. We have several techniques. The deletion, either you delete it out, right? And this is actually only when there are just few of them before you delete it. We have the imputation, either you fill them by your mean, your mode, or your median. Then we have the interpolation, estimating. That's the act of estimating the missing values using surrounding data points, like linear interpolation. So these are the different techniques you can use to fill in the missing value. Um, I think I may have. Okay, we have time series decomposition. Yeah, this is actually the breakdown of your series into its components: the trend, the seasonality, and the residuals. And we are going to see this too in our project. Then we have the additive model, which assumes that the data is the sum of these components. Then we have the multiplicative model, which assumes that the data is the product of these components, right? That's the formula you're saying, the trend. For additive, it's saying that the data is as a result of adding the trend, the seasonality, and the residual, while multiplicative assumes that your data is as a result of multiplying all those components together. So the composition helps us analyze each component separately, involving our understanding and forecasting. Then we have the smoothing techniques, which remove noise to reveal underlying patterns in the data. Yeah, we also see this in our project in a bit. Then we have the moving average, which calculates the average of different subsets of the time series. We have the simple moving average, which gives the which gives equal weights to all values in the window. Then we have the weighted moving average. So all these are just smoothing techniques. You saw that chart, or if you can just picture it again, it's kind of a bit rough. But if you apply any of these smoothing techniques, it will make that line smooth. And we are going to see that in our project too. Then we have the exponential smoothing, right? Which gives more weight to recent observations with methods like simple exponential smoothing and hot linear trend model, hot winter seasonal model. So they all have their own parts to play and the kind of data you're working with. I'm rushing because we're already in time. We have the feature engineering, which we all know involves creating new features from existing data to improve the model performance, rolling statistics, dates and time. You can extract the year, month, and day from your dates column and probably make use of it. Then we have okay, this is just a case study, just like a walkthrough, right? So imagine you have a daily sales data for a store. So first you load and inspect the data set to understand its structure. You clean the data by handling duplicates, outliers, and inconsistent entries. Then you transform the data by using scaling and normalization. You resample the data to a different frequency if needed. Then you handle missing data using imputation and or interpolation. Then you decompose the time series to analyze its components. Then you apply smoothing techniques to review patterns. Then you engineer new features like lag features or rolling statistics. So this is just a walkthrough of the process you can take on your data set just to make sure it's properly prepared for prediction. Okay, so yeah, this is where our slides end, and we're going to jump into the notebook. Does anyone have any question so far?
Yes, I do, sir. Can you hear me, please?
Okay, I can hear you.
Okay. I read it in the material that before you can work on a time series data set, it it should be in the data set must come as a non-stationary data. Then you convert it back to stationary. So I'm
Yeah,
kind
say
of confused.
you- yeah, please go
You
on.
said what? You said what?
No, no, go on. You said you're kind of confused. You're about to make a
Yes,
statement.
I'm kind of confused in the sense that you can't work with it if it is stationary, but you still have to convert it back to stationary if it is not stationary by using the smoothing techniques. So I don't know, like I don't know why it's in that way, or is it that my interpretation is kind of different?
Not sure. Can you take that question again? Are you asking what is the question exactly? Are you asking why we change it, or is there need to change it to stationary or something?
Yes, like I want to know if the procedure requires to change from stationary to like
Okay.
if the data comes as a stationary data, is it possible to use it for time series? And if it comes as a non-stationary data set, like why do we need to change it back to stationary since the law says you can't use the stationary data set for time series?
I'm not.
Or
Did
am
you
I
say that is
interpreting
the
it in the
law?
wrong way?
I'm not sure that is the law. I mean, I have not said something like that, but my knowledge I have about that is there are some models that works with stationary data, like ARIMA model. If you give it an unstationary data, it's not going to perform well. So yeah, Prophet model works very well with I mean it can adapt to time series that is not stationary. Yeah. But it's the process. You need to make the data stationary, right? Before you go
Okay.
into the prediction. Yeah, that's actually a process you need to take. So once you check that it's not stationary, yeah, you need to make it stationary, right? And I think it will also help to reduce all the noise and everything. Yeah. So it's the process you need to also take, make it stationary there before you use it for prediction.
Oh, okay. Thank you.
Yeah. All right. I think I'll just have to go to the notebook so that we can spend some time there. Let me quickly share my VS Code. Okay, we are back to our notebook and we still have a lot of things to cover. this is where we stopped. And yeah, I knew that we were using we're using British pound and Egyptian pound in our last class, but we were not supposed to use that because of some of these statements that were already in the code. They are just predefined statements using metrics that were already calculated for USD and Indian rupee. So pardon me for using the one we used in our last class, but it doesn't change anything. It's just the same format. My point is the whole explanation I have in this notebook was actually for all these write-ups and everything was actually for USD and Indian rupee, not the Egyptian pounds and British pound. So I'm just going to quickly change it back to that. Again, it's just the visuals that will change, but it's the same process that we're taking. Like I told us, this code is just an automated code in a way that you can always change it to whatever exchange you want. So I'm just going to stand here because this is where I want to start. This is where we stopped. I'm going to stand here and then run all the code above. Okay. Um, I'm waiting for the inputs box. So I'll put in my USD. So for those of us that are probably new to this whole stuff, you may want to watch the previous video to understand what we are doing here, because we've gone far and I obviously cannot go back and time is not on our side. All right, so this
Yeah,
was actually the
and if
chart.
we can also share these changes that you're making to the notebook, if you can also share it, we appreciate it.
Okay, all right, that's fine. Okay, so I was about to explain this chart before we ran out of time in our last class. But yeah, the weekly function, like I said in our last class, what it does is to plot that data that was downsampled to a weekly granularity. Yeah, this is it. Right. So if all these parameters are set to true, which they are, it will present other visuals. So this is it's plotting just the closing price only. Here it involves the closing price, that's the open, the high, the low, and the close. Right. And also, just so you know, we actually handled missing values for the closing price only, since it is our target variable. We did not touch anything on the other ones, right? Considering that it's the finance data and the rest of it. Not like we can't do anything, right? But we chose not to touch anything. So this is just the closing price. This is just what the curve looks like, and you can also see that it's on a trending side, right? And it seems to have a kind of a pattern. If you are saying, look at it comes, it goes up, it falls, it rises, it falls, it rises, it falls, it rises, it falls, it rises. I mean, this is you inspecting it using your eyes, right? Then we have the density plots, right? So on this density plot, the x-axis represents the closing values. This is the x-axis, and it represents the close price, that is the closing price of that data set we plot. While the y-axis represents the density, which indicates the probability distribution of the close price. Okay, so this plot is actually bimodal. It has two peaks. It's bimodal, showing two distinct peaks, right? So the first peak is around 45, right, indicating a high concentration on the close price values. Then the second peak is around the 65. So the presence of these two peaks suggests that the closing price have two dominant ranges or regimes, right? And who knows, maybe something happened that affected the market as of this when this peak went up, maybe something happened. So this could be due to different market conditions or other factors influencing the price. So yeah, it's bimodal. Then we have the autocorrelation plots. Um, okay. So the x-axis represents the lag, number of time periods, the lag. So it's like comparing the present data with the previous data. So this is the lag. This is 200 weeks, 400 weeks, 600 weeks, 800 weeks ago, right? Then the y-axis represents the correlation, autocorrelation. So it starts as at a very high value at lag 0, yeah, and gradually decreases as the lag increases. So as the lag increases, the correlation is actually decreasing. So when it's comparing present value with previous value, the correlation is decreasing. It becomes a negative value at some point here. Yeah, so you may be wondering how this is of relevance. So this is actually a decay, it's decreasing. So the gradual decrease in this autocorrelation indicates that the influence of the past prices diminishes over time. It had greater effect as of this period, but as time goes on, the effects the past price is having on the present price is decreasing, right? But yeah, there is an increase here. So it's saying in a way that prices as of 800 weeks ago is beginning to have a higher correlation. But I mean, you can always do more research on this. Yeah, it's actually an interesting graph that can show you more insights to it. So this is just an autocorrelation plot that can also give you insights to your data, right? So yeah, that's it for some visualization on the data set, the exchange we are working with. All right. I think there's can this be executed on Jupyter Notebook? Also, this is a Jupyter Notebook. Oh. I'm not, this is a Jupyter Notebook. It's a normal notebook, but I'm working locally. I'm not doing anything online. Yeah, it's a Jupyter Notebook. I think I'll have to host it on a drive before I can share it across because right now it's on my local device. All right, so this is just an explanation, blah, 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 but I've explained all the stuff in details. Yeah, I talked about it not being normally distributed. It's bimodal, right? So this is actually where we now then do the whole stationarity of a thing. We try to make the chart stationary, right? And we also do that using putting some tests in place. So we have a function that tests for stationarity. If the data is, let me look at the function before I make any statements. Yes. Yeah, it presents if the data, I mean, it's going to give us a result, the Kifula test. This is the result. And it is from this result that we are going to know if the series is stationary or not. But then again, this is actually the plot. So the blue one is the original time series. I think I should minimize this a bit. Yeah, this is the original time series, the blue one. While the red line is the rolling mean. We talked about smoothing, right? So this is the rolling mean. Then this is the rolling standard deviation. So let's look at the function. Yeah, it does the whole time series. It does a 52 weeks rolling mean and rolling standard deviation, and we put that into a visualization. So that's just what we have here. And yeah, so that's what that chart is showing us. Then we have the Dickey-Fuller test. So all these minor spikes in this I think it's volatility they usually call it. We have it in 2.8, we have it around 2.13, 2.18. But it's not that visible. Most times when it is high, it's probably that there's something that happened that make the price go that makes it goes that way, right? Let's look at this Dickey-Fuller test because this is actually where our interest lies more. So we have the test statistics. We have the p-value, the numbers of lag used, and the number of observations, as the number of entries, the critical values, and the rest of them. So the test statistics, this one, this guy here, I'm trying to interpret these results. This is the Kifula test. This is where it's coming from. Okay. This test statistic is usually compared with these three critical values. It's usually compared with these three critical values to determine stationarity. So if this test statistics right now is less than the critical values, right, that it is more negative than it, we reject the null hypothesis, the null hypothesis of a unit root indicating stationarity. And as it stands now, this value, you should know that 0.2 is bigger than 0.3. For those of us that are not aware, 0.2, right, is sorry, minus 0.2, just so you know, is actually bigger than minus 0.9. No, wait, what am I saying? Am I getting it right? The closer the negative value is to 1. Yeah, this is far away from 1. Yeah, I'm correct.
Yeah,
So
correct. Yeah.
it's confusing. Yeah, I'm correct. So minus 0.2 is actually bigger than this. Yeah. So it's being bigger than this now. It means that this data, this our series is not stationary. All right, it's not stationary. Then the p-value indicates the probability of observing the test statistics under the null hypothesis. So the high p-value, which is this 0.929 we are having here, suggests that we cannot reject the null hypothesis. That we cannot reject that it is not stationary. So because it's very high. So the critical values, like I said, is what we use to compare with our test statistics. So they represent threshold at different confidence level. So since this actual one now
Sorry. Sorry, can you come again? You said if the test statistic is less than
is greater
the
than,
critical oil, oh,
is
greater
greater
than.
than,
Okay,
yes, it means
okay,
the data is not
okay.
stationary. Yeah, so since this test statistics minus 0.27 now is actually higher than, that it is less negative than these other ones, all the critical values. So it lies with, it means that the data is not stationary, right? So the time series has a trend and relatively stable volatility, right? We can see that by the rolling mean. I mean, the rolling mean is going on a high side. Even the standard deviation is, you can see some spikes a bit here. All right, so now that we've seen that the data is, I mean, we've seen how to kind of interpret this and know how to know if it's not stationary or not. The next stuff, okay, this is the statement about it. Okay, I'm going to take this stuff. Somebody is waiting. So here is the next thing we did. We did decomposition. So we have a function that does the decomposition for us. Okay. So we're looking at the targets variable, the closed column. Okay, so this is what we have here. So we have the trend, seasonality, and the residual. This is the function we are using to work on that. So it takes in the closing values, and we are using a multiplicative model here, right? You can always change it to see which one works better. Okay, so this decomposes the time series into component parts using a multiplicative model. And we say multiplicative model, it assumes that it is the multiplication of this three stuff here 1, 2, 3. It's the multiplication of the three of them that will result to this. That's what this multiplicative model assumes. Okay. So we have the trend, the long-term movement in the data. Then we have the seasonal, the repeating short cycles. So this was that small pattern we were saying. This is the repeating short cycles we have. Then the remaining variation after removing this guy and this guy, this is what it remains in the data. So yeah, this gives you an insight into the data set to see what the each component of that time series looks like. So it's, I mean, let's try to interpret this. Let me just say it. I just hope you understand. You can always do more research, right? So looking at the trend, let's talk about the trend analysis. The trend components indicate that there was a stable period. It was actually stable in the early years, 2.4, 2.5, 2.6, 2.7, 2.8. It was kind of stationary, right? But there was this spike in it as of 2013. So a lot of things must have caused this, right? So it's actually crucial. You know what happened, and it can actually also be helpful in your analysis. Maybe let's say it's who knows, maybe it's the period that range usually for. You may need to factor that in, but it doesn't look like a weather something because it's not repeated over the year. But yeah, it could be as a result of something. Then we have the seasonality analysis. So it shows a regular predictable pattern that repeats annually. So this is the pattern in data that repeats annually. So it can be leveraged for seasonal forecasting and planning. Then we have the residuals. These are actually the parts of the series that cannot be predicted, right? So it appears to be a little bit random. All right, so that's just the components of the time series. Let me zoom out. Time is already running. We have only 1 hour and we are still far behind. All right, so the next thing, uh, okay, the next thing we have is where we convert it to stationary data. Yeah, we do the conversion. So we have a function that does that for us. We use logarithm to do the conversion for us. So logarithm transformation helps stabilize the variance in the data and make the data more stable, more stationary by reducing the effects of larger values. So that's why we're using the logarithm method here. So it's actually very useful in time series data. And it changes the variance and deal with those higher values, right? Then after we must have done the conversion, or sorry, after we must have transformed it, we now then look at the rolling mean like we did in the previous one to check. And this is what the rolling mean looks like, and this is what the standard deviation looks like. So you see that the data is more stationary after applying that transformation on it. Okay. So the next thing we have is the part where we now work with the model. We split the data for training, right? We split the data for training. We actually used 90 10. So our training data set was 90 and our test data set was 10. So we have a function that does that for us. So we just need to unpack the results. So yeah, this is the whole transformation. This is where it's calculating the length. Yeah, this is where it splits it into 90 and 10. This indexing, just in case you're confused, this is indexing, slicing it to separate the training and the test data sets. Okay. Then we visualize it. So what we are saying here, the blue one is actually our training data set. Then from here is our test data set. So when we do prediction, we're also going to see if it makes any sense. I think I should be running this because I changed. Let me see if this is still USD. Okay, just in case. Okay, so yeah, it does that for us. Now here is where we use auto arima. Here's where we use auto arima model. So this is a whole lot of write-ups that we may not have time to read. But what we are looking for using the auto arima are these values, P, D, Q. So P represents the order of auto-regression, D the order of integration, and Q the order of moving average. So it's from this auto arima that we are going to get. It's like hyperparameter tuning, right? We are trying to get the best possible um arrangement, right? So it is from this auto arima that it will determine which best parameter would be useful. Okay. Then when we get it, we now then use it on the main model for prediction. So that's what is happening under this function you have here. So what the function does, let's see. So we have the PDQ. These are global variables. We set them to 0. Okay. Then we have the initialization of the auto arima. Okay. So it takes the training data, which we are going to pass in. The start time, the start P and start Q is set to 0. So these are the initial values of P and Q for the grid search. Then how do we want to test? So we are using the Kifula test, augmented Kifula test to determine the optimal values for D. Then we have the max P and max Q, which is the maximum values for P and Q in the grid search. So we are just going through it 3 times. You can actually increase this. Like I said, this is like parameter tuning. Okay. Then we have the frequency of series. So 1 for non-seasonal data. So if the seasonal data, you set it to 0. Then D is set to none. So this actually means we want the model to determine the optimal value of D. So let the model determine D. Then is the seasonal is set to false. So this actually says that the data is not seasonal, right? So yeah, what else? Sorry, let me let someone in. This is actually not going to be used because these are actually the initial values for seasonal components. Yeah. Then trace equals to true. This prints the progress, this output you are seeing here as it's going through it. Then error action to ignore it, suppress warning. Then use a stepwise search to reduce computational time. Then after we've done that, we print the summary of our auto arima. So it's going to the summary of the fitted auto arima, which is what we have here. So it includes some statistics, some values that will actually help us in our main model. Then what we now then do here, we unpack the PDQ to the global value. Those ones we initially set to 0. We get them from the model order. So once you do model arima.order, it's going to unpack this value you're seeing here. This is actually what we are looking for, the PDQ. So it's going to unpack it into these variables out here. So this is just going to show us our results. Okay. So let me see if I can still remember how to interpret this. AIC, letting the full meaning something archaic information. criterion thereabout. But this is the process. It's well, I said the search process, right? Using AIC. Then after all said and done, after the whole search, these are the best values it got for the PDQ. These are the values it got for the PDQ. Okay, I think I wrote a note on this. Just give me a sec. I'm coming. Okay, so um let me try and interpret some of these things here. Just give me a sec. All right. So this is PDQ. All right. This is the dependent variable Y. The model we're using Sarimax model. The date it was run, which was today, the time, the sample, the number of observations, the coefficient, standard error, the z-value, this is statistics, the confidence level. Okay, so this is actually what we're after. Let me look for the notes where I wrote that stuff. Okay. So P being one indicates that the model uses one lag value dependent variable in the regression model. Okay. Then the definition already was here, the order of integration, the moving average, PDQ. So D being one, this indicates that the time series has been differenced once to make it stationary. It has been differenced once to make it stationary. So differencing is actually a technique to remove trends and seasonality by subtracting the previous observation from the current observation. Okay. Then this P, which indicates that the model uses one lag value of the dependence variable in the regression model. So in other words, the model includes the immediate past value to predict the current value. Then this one that is set to 0, this indicates that no lag value of the forecast errors are included in the model. That is no moving average terms. So the moving average is not actually used in the prediction. It's essentially not used in the model prediction. We are actually running out of time. Okay, so yeah, like I said, we are after this. And once we get to this value, it's actually what we're now then use in our main ARIMA model. Oh, we have some visualization here. This is coming from the plot diagnostic. Standard residual. This shows the residuals from the ARIMA model over time. So it appeared to be centered around 0, which is a good sign. There are no obvious pattern or trends indicating that the model has captured the underlying structure of the data. Right. However, there are actually spikes, which might indicate occasional outliers or period of high volatility. Then we have the histogram plots with some density plots on it. So let me just summarize this. This is centered around 0 with no clear pattern suggesting a good fit. Okay, while this is approximately normally distributed, unlike the previous one we saw that was bimodal. So this is normally distributed, though there might be slight deviations in the tail. Then for this guy, it follows, you see this red line, the data point seems to follow the red line, right? With some deviation at the extreme. So this is also probably indicating those high values. But yeah, it tends to follow this line. Then this parallelogram, yeah. The residual shows no significant autocorrelation, indicating that the ARIMA model has captured the data structure effectively. Okay, so Yeah, this is coming from the plot diagnostics. You can do more research on how this can be helpful to you. This was when we ran this. Was it? Yeah, this was when we did our own. We had to just save all the stuff then. And there are some notes here. We will not have time to go through it. Oh, a whole lot of theoretical concepts here. Mm, You have to pardon me. I did not do this project alone. Yeah. Mm. So I'm seeing some big terms here that actually one of our colleague understood better. Yeah, but this is actually an explanation to some of those results we saw earlier on. Probably when I share the notebook with you, you can get more insights to it before I start calling names, calling words that will cut my tongue. All right, so um, yeah, this is actually where we now train the ARIMA model itself. Okay, using the PDQ, though you are not seeing it here. Like we are saying, all the cells are function. So this is the function. This is what it's doing. So using the ARIMA model we imported, it takes in the training data set. And remember our variable has been saved to PDQ. It was unpacked. And we are using the global variable. So it's no more holding this 0, 1, 1. It's holding 1, 1, 0. So it was passed in as the order. Okay. Fit the model and we do the forecasting. Turn it into a series and then we visualize it. Okay. So this result is similar to the other one with another new information down here. But this is a prediction. Yeah, I mean, it doesn't really make any sense, but this this is what it's predicted for us. That's what it's predicted for us. All right, so I'm going to stop here and allow us to ask questions. This is the result. Then in our next class, we are going to, because we actually use Prophets to do this prediction, and it gave us something a little bit different. And when we compare it, it was actually a little bit smaller. So I'm going to stop here. In our next class, we'll just continue from here. So does anyone have any question for me?
Yes, sir.
Yeah, I can hear you.
Okay. I understand that the close is the target variable, but I need to
Yeah,
understand. Did you use? I said I understand that the close column is the target variable, right?
okay.
So I want to understand if you used the rest of the columns as the features, or you selected the date column alone and probably one other feature, because I'm trying to understand how you did the splitting, like choosing the X and Y. So I'm like kind of lost in between.
Okay. Let me trace it back. I need to confirm that before I answer that. Because I know we have a univariate time series and multivariate time series. So let me see. Mm, Please, I'm coming. Let me see if I can trace it back. Though our time is out. But I think this is a univariate analysis. Yeah, it's a univariate analysis. We are using just the closing price. Yes, we are using just the closing price for that prediction. Yes, this is it. After decomposing, this is where we convert to stationary DF log. Yeah. We are using, sorry, yes, we are using only the closing price for that. So it's a single column prediction. Do you get that?
Yes, I understand that the close is the target, but what did you use
Yeah,
for
yeah.
the okay,
So I'm saying we, I think in our last class we saw that there are two time series analysis. We have the univariate analysis where it's just your dates and your prediction, your targets variable. That's a univariate analysis.
oh,
Then
okay,
we have the multivariate analysis where you can include all these other ones to help predict it. So I'm saying for
oh,
this
okay,
project we did here, we used only the closing price.
the
So all
close,
these these other ones was not included. So yeah,
okay,
that's another thing you could take on. Maybe do multivariate analysis where these ones are included. Yeah. So it's a single variable.
oh, okay, thank you.
Okay. Any other question? I'm already out of time. All right. I'm seeing a runtime error optimization. You may just want to put that online and see the results you have. Maybe someone and solve that. Okay. This is it. So in our next class, it's just remaining few. So I think we'll have some time to look at the app we built. That's if it's even up and running. But yeah, we're almost at the end of the stuff. So we're just going to summarize and look at some findings and we'll call it a day in our next class. All right. So it was nice seeing you around here and nice coming around. So I look forward to seeing you in our last class. This will be on Monday.
So please, can we get the listing of this the notebook?
Yeah, I'll upload it to a drive. It's actually large, so it's in a zip file, and then in our last class, I'll just say it with us.
Okay.
Yeah. All right.